Am I going? I think I'm going. All right. Yes, it's running. Good deal. All right, so chapter 4 is about selection structures. Okay, so let's take a look. So here in this chapter, we'll introduce the concept of control structures and what those things are. And then we'll take a look, and this chapter focuses on selection structures, or a lot of times we'll call these like conditionals or if statements, all right, for the most part. So we'll take a look at these things called relational operators, right? And then we'll also look at logical operators and different forms of the if statement, okay? And we'll look at some logical or Boolean expressions and see how those things work. We'll also take a look at how to do things, how logical expressions work with the string type. And there's this concept called short circuit evaluation we'll talk about. And then there's a few other things. There's this thing, this conditional thing, this question mark colon thing. We'll take a look at that, how that works. I don't use that very often, but it's something that C++ has. Now we'll look at the switch statement and the assert function. Okay. All right. So far, we've written all our programs using basically a sequence of instructions, right? So you do one instruction, and then after that instruction is done, it goes to the next instruction, and then the next instruction after that. So it's a sequence, right? So that works great for a lot of situations, but if we want to be able to write more interesting programs and have a little more flexibility, we can use some of these control structures, okay? And so these include things like selection structures and repetition structures, which are like loops. And so chapter 5 deals with loops. And then chapter 6 covers functions. So the idea with the function is that you can, be going along in your program and then have it skip to another part of your program, do the stuff that's there, and then skip back to where it was. So we'll do that. We've already used some built-in functions, some predefined functions like the power function, right? But chapter 6 is about that. So in this chapter, we're going to focus on selection structures. If you're into more visual types of aids and stuff, so we can write things and draw things like flowcharts, right? So we've talked some about pseudocode. Pseudocode is just English-like instructions to help you plan an algorithm. Another thing that you can do to help plan an algorithm is draw a flowchart. And so here's just kind of flowchart examples of the different control structure types that we're talking about. So sequence of instructions is just one instruction after another. Selection structure would be like this one over here, where you've got some kind of expression, right? And then it evaluates to true or false. And if it's true, you do one thing. And then, or it could be multiple statements, right? But if it's false, you do something else as an alternative. Or it could be multiple statements that you do there. Sometimes we have a true path with no false path. And sometimes we have a true path and a false path. So we'll look at different versions of that. And then a repetition structure is kind of like a selection structure. You have this condition or this logical expression that evaluates to true or false. But instead of branching, as long as that condition is true, you repeat stuff. And so you keep repeating things until the expression becomes false, and then you go on to the next thing. So we'll do that in chapter 5. All right. So a selection structure is basically just, it's something that you have a test and evaluates to true or false, okay? And so this test, we call these logical expressions, or sometimes we call them Boolean expressions. They're something that you have some kind of test that's going on, and it's either going to be true or false. There's two possibilities. So, and that's not C++ code or anything, obviously, but 8 is greater than 3. Is that true or false? Well, that's true, right? So to write logical expressions in C++, These are the main relational operators that we have. So relational operators are used to test the relationship between two things. And so all of these relational operators are what we call binary operators. Binary operators, that just means there's something on the left-hand side and something on the right-hand side, okay? And so what's on the left and right-hand sides is some expression. So it could be just something simple like a number or a variable, or it could be a longer expression like an arithmetic expression or something like 8 plus 2 times 4, something longer like that. So it would evaluate the expression out and then compare the results of the expressions. So these are the main relational operators that we have in C++. The first one is equal to. So notice it's 2 equal signs, right? Not 1 equal sign. So you have to make a mental note of that right now. When you're comparing two things to see if they're equal, it's 2 equal signs. Okay? 1 equal sign means assignment. You're assigning the result of something to like a variable or something. Okay? So we have equal to, we have not equal to, which is the operator is an exclamation point and then an equal sign, so not equal. Then you have less than or equal to, right? So that's how you have to write it, less than, equal, right? There's no key on the keyboard that has a less than sign with a line under it or something like that, right? So less than or equal to, greater than or equal to. All right. So real quick, some examples here. And so these are pretty straightforward, I think. 8 is less than 15. Is that true or false? Well, that's true, right? 6 is not equal to 6. That's false. It is equal to 6, right? And 6 is equal to 6. That's false. 2.5 is greater than 5.8. That's false. 5.9 is less than or equal to 7.5. True. And 7 is less than or equal to 10.4. That's true, right? So that's what we're talking about here. So, it's comparing two things to see if they're equal, less than, greater than, or whatever. All right, so that's comparing numbers. You can also do things like compare characters, right? So what's it going to do with characters? So remember, we've got this thing called the ASCII character set. And there's a ASCII number. There's a number that corresponds to every character in the ASCII character set, right? So the capital A, for example, is a 65, right? And also, remember, there's the digits, the numerical digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are also characters in the ASCII character sets. But what's stored for the character digits is not the same as the numbers, right? So I'm trying to remember. I can't remember. We'd have to check it. I don't think we have that. In your book, I'll notice it in your book in chapter 4, on page 190, there's an ASCII character set there. But the digit 0, for example, has an ASCII value of 48. And the character 1 has an ASCII value of 49. So that's what is actually stored there. Okay? So if you were doing something like capital R is greater than capital T, what's that actually doing? So capital R has an ASCII value of 82. Capital T has an ASCII value of 84, right? So it's actually comparing, is 82 greater than 84? No, it's not. So that's false. Right? And so there's a somewhat logical order to the ASCII character set, right? Notice the digits 0 through 9 come first. They have ASCII numbers 48 through 57. And then they've got a few other things. But then you've got all the uppercase letters, right? And they're in order, right? So 65 all the way through 90. And then there's a few other characters in there. And then starting up at 97, that's where the lowercase letters come, right? So the uppercase letters are always lower have a lower ASCII value than the lowercase letters, right? So that's something to point out. One thing I should mention, we say, logical expressions evaluate to true or false, right? What's actually being returned there is usually like a 1 for a true. Some kind of positive number means true. So we usually just say 1 is true, and then a 0 gets returned if it's false. That's how it actually works. So just kind of make a mental note of that. 1 is true and 0 is false. All right. And in the book, they have more examples than we have on these slides. So you definitely need to be reading over the book, the chapters in the book as well. Okay. All right, so let's look at some different forms of how we could actually write stuff. Just real quickly. So we have these logical expressions, that evaluate to true or false, but to actually use them in our C++ programs and as code instructions, we need to do something like have them as an if statement. So the way that you do that, you have the word if, and then inside of parentheses, your logical expression that we're talking about that evaluates to true or false. Okay, and you have to have that outer set of parentheses. Okay, so we have different forms of this. We have this one's called a one-way selection. So one-way selection is an if statement that has a true path but no false path. So here, for example, if that expression is true, it's going to do what comes next. But if it's false, it just goes on to the next statement after the if statement. And they mention here that these terms, decision maker, so the expression is the decision maker, that's the logical expression, and then you have your action statement afterwards. Flowchart wise, it would look like this. So you can see there's a true path, but no false path. If it's false, it just goes on to the next statement. We could have a two-way selection. In a two-way selection, there's a true path and a false path. So it would look something like this. If, and then your expression that you're testing, if that's true, you do what comes next. But if it's false, you've got this thing called an else. So it skips down to the else and does that instead. So you have a true path and a false path. So there you go. There's your flow chart. So you can see there's a true path and a false path. And they have some examples in the book, and we'll be writing some examples as well. One thing I should point out, they mentioned in the book, but they don't have a slide for it. Let me see here. I'll just see if I can write it this time. So just about the time you get used to putting semicolons places, there's places where you don't put semicolons. Okay, so like if you're writing an if statement, if x is equal to, two equal signs, 5, it's like that. You do something, whatever it is, see out. My writing's horrible, sorry. Blah, right? So notice there's not a semicolon after the if part, right? So if you were to accidentally, if you put a semicolon there, what would happen is it wouldn't give you an error on that. It just wouldn't work right. So on this particular situation, it would test this. If x is equal to 5, if that was true, the semicolon will tell it just don't do anything. There's no action statement there. And then that next statement, see out or whatever, that would always get done. So that's one of those easy mistakes to make. So be careful on that. So no semicolon, okay, on that. All right.
So on any of these expressions, no semicolon?
Right. No semicolon after the expressions on an if statement. Let's see here. So they mentioned earlier versions of C++ didn't have this thing called a bool data type, but then they added that at some point. So the data type bool, B-O-O-L, it's a data type that you can use, and you can assign the words true or false as possible values. Right? So that comes in handy for some things. I think they have an example here, and they definitely have examples in the book. What actually gets stored there is like a 1 for a true or a 0 for a false. I think there's some examples a little bit later on a later slide. All right. So let's look at, so those are relational operators, right? Relational operators test the relationship between two expressions, right? But you're somewhat limited, you know, what you can do with those. If you want to write more complex logical expressions, you can kind of chain logical expressions together to form a larger logical expression. And we can do that with logical operators. So you've got your relational operators, like greater than, less than, equal to, those. And then you've got your logical operators. And these are the three main logical operators that we're going to be dealing with in this class. We've got the not, we've got the and the or. Okay? So a not is just an exclamation point. And I'll show what that does in just a second. But basically, the not will just take the opposite of whatever the logical expression is. The and, you can use that to combine two logical expressions. And then the or is the same way. So the not is a unary logical operator, meaning that it only has one operand. So it's the not and then something next to it on the right. The and and the or are binary operators, so there has to be something on the left and something on the right. So the and is two ampersands, okay? And then the or, you do the or with two pipe signs, right? So that might be a key that you may or may not be familiar with. The pipe sign is usually on the same key on your keyboard as the backslash, not the forward slash, but the backslash. Right, so it's just like the vertical line. On some keyboards, it might be like it might look like this. It might be like a vertical line with a dash in the middle, a little gap in the middle or something. But it's two of them, right? There's actually operators in C++ that's one ampersand and one pipe sign, but they do different things. Those are the bitwise operators. So we're not using those. Right? So let's talk about how these things work. So have you ever seen a truth table before? All right, so if you're a math major or a computer science major, and maybe engineering, I'm not sure about engineering majors, you may end up taking some kind of class in discrete math, like discrete structures or discrete mathematics. And in that class, you deal a lot with expressions, and it's kind of one of the first proof classes usually. But you'll do some stuff where you show some truth tables. But anyway, here the truth table, basically what it does is it will show all possible combinations that you could get with this type of expression. Okay, so the not is pretty easy. So if you look at the truth table for the not, on the left is the expression, like the original expression, and on the right, that shows us what the result will be if you put a not in front of it. So a not is super easy. It just takes the opposite of whatever it is. So if the expression evaluates to true and you do not true, you get a false, right? If the expression evaluates to false and you do not false, well, that's true. Not false is true. So down at the bottom, you see a couple of examples. And so you always do what's inside of parentheses first, right? So there we have not A is greater than B. So A is greater than B is going to look at the ASCII numbers. So is 65 greater than 66? Well, that's false, right? It's not. But then we have not false. So not false is true, right? And on the second one, 6 is less than or equal to 7. Well, that's true. But not true is false. Good. So not as easy. How about and? So with the and and the or, we have two expressions. We have something on the left and something on the right. And so we see on the truth table, the only way to get a true using an and is if both things are true, right? So true and true results in true. True and false is false. False and true is false. And false is false. My silly little real world example that I tell sometimes, it goes something like this. So like growing up in a small town, we had like one place to eat, and that was Dairy Queen. And so suppose when I was a kid, my parents told me something like, okay, well, if you do your homework and you clean your room, we'll take you to Dairy Queen for ice cream, right? So how does that work? So I have to do both things, right? I have to do my homework and clean my room in order to get ice cream. So if I do both things, great. It's Ice Cream City, right? But if I don't do one thing, so suppose I did my homework, but I didn't clean my room. Well, that's not good enough, right? I have to do both things. So that'd be like a true and a false. And so no ice cream. Or if I didn't do my homework, but I cleaned my room, that'd be like a false and a true. Still false, right? No ice cream. If I didn't do anything, if I didn't do either, I definitely wouldn't get ice cream, right? That'd be like false and false, right? So anyway. So here's some code examples down at the bottom. 14 is greater than or equal to 5. Is that true or false? That's true, right? So, hey, check this out. Let's see if I can do this. So 14 is greater than or equal to 5 is true. And A is less than B. That's true. All right, so true and true gives you true, right? So the result is true. And you can see the result there, obviously. How about 24 is greater than or equal to 35? That's false, right? and so actually we already know what the result's going to be, right? False. So it's going to be in one of these two categories right there, right? False in anything is false. But if you're curious, A is less than B, that's true, right? So false, my F is not working right. False and true gives you false, right? But so like I was saying, that first part was false. So we already knew what the result was going to be. And in fact, that's how the compiler evaluates logical expressions. As soon as the compiler knows what the result is going to be, it doesn't even mess or waste time evaluating the rest of it. It will finish evaluating it. And there's a term for that. It's called short circuit evaluation. So short circuit evaluation just means that once the compiler knows what the result's going to be, it stops. Right? So that's an and. Both things have to be true. And or, with an or, only one thing has to be true. Okay? So true or true gives you true. True or false gives you true. False or true gives you true. The only way to get a false out of an or is if both things are false. False or false is false. So the ice cream example, I would only have to do one thing, right, to get ice cream. I could either do my homework or I could clean my room and I would still get ice cream. If I do both things, great, I get ice cream. But if I don't do either one, then no ice cream. Right. That was not some kind of childhood trauma memory or anything. That was just my silly example. All right. So that's an OR, okay? And this is what we just call a regular OR. There's something else called an exclusive OR. Have you ever heard of an exclusive OR? So an exclusive OR, with an exclusive OR, one and only one true will give you a true. Like if both things are true when you do an exclusive OR, then you get a false on the true or true XOR true. But we're not going to do exclusive ORs in here. This is just a regular OR. All right, so here are some examples. 14 is greater than or equal to 5, right? That's true. So you know true or anything is going to give you true. So we know what the result is going to be. A is greater than B is actually false, isn't it? But true or false gives you true. 24 is greater than or equal to 35. That was false. So we have to look at the other part. A is greater than B. That's false as well. So false or false gives you false, right? How about this one? Capital A is less than or equal to lowercase a. Again, it looks at ASCII values, right? So it's like 65 is less than or equal to 97. Is that what it was? So that's true, right? And true or anything gives you true. 7 is not equal to 7. That was actually false, right? But true or false gives you true. Good. So that's the logical OR, right? They mention here about some things about order of operations. So in general, things are evaluated from left to right, but parentheses will always change the order. But here's your order of operations for everything that we've done so far. So actually, the first things that get done is like the not, but again, you always do parentheses first, right? So if there's parentheses, you do that first. Plus and minus up there at the top, that means like a positive or negative. That's what that's talking about. And then comes multiplication, division, modulus, and then addition and subtraction. And then all your relational operators, like less than, greater than, less than or equal to, and all those. But here's one thing that's important to note out, is that ands take place before ors, right there. So you do ands before ors if you have a combination of things. I wish they had a slide of an example. So here in the book, they actually have an example. Let's see if I can do this. It was page 201. 11 is greater than 5. Or 6 is less than 15. And this is how I do my ands, because I can't make the fancy ones. Mine always end up looking like treble clef signs. 7 is greater than or equal to 8. Did I get it right? All right, so how does that work? So if you evaluate that out, right? 11 is greater than 5. Is that true? That's true, right? So you got a true, or 6 is less than 15. That's true. However, and you have an and. 7 is greater than or equal to 8. That's false, right? So you're looking at that. True or true and false, right? So that's an easy mistake to make, like if you were to see this on a quiz or something like that. You might think, oh, I just do these in order from left to right. And so if you did that, which would be wrong, true or true gives you true. And then you'd have true and false, which is false, right? Right. But the order of operations says that ands take place before ors. So this comes first. So true and false is what? True and false is false. So then you do the or. True or false is true, right? So the result is true. So that's worth noting there. All right. All right, so let's see here. So here's some more examples. Let's look at these. So suppose we have these declarations. So we've got some variables here, right? And these examples start over there on page 202. So suppose we have these examples, or these variables. So found is a Boolean variable, and its value is set to true initially here. Age is an int, and it's equal to 20. Hours is a double, and it's 45.3. Overtime is a double, it's 15.0. Count is equal to 20, it's an int, and then ch is a character, and it's equal to b. So given those initial values there, what are the results of these expressions, right? So, and again, you might have to refer back and see what things are. So found was set to true, right? So if you're looking at not true, that is false, right? So that's how that would work. Hours is equal to 45.3. So just plug in, 40. It's going to compare 45.3 is greater than 40. That's true, right? How about this one? This one's a little weird. This would actually work, but I probably typically wouldn't do this. So the third one, not age. They say the result of that is false. So how does that work? So age is an integer variable. Age is 20, right? But I mentioned earlier, as far as like true and false goes, 0 means false. I said 1 means true, right? But technically any positive number can also mean true. A non-zero positive number is true. So that would actually be not true, which is false. So that's a little weird, and again, I wouldn't suggest doing that, but that's how it works. How about this one? We have, not found. We said that was false, right? So not true is false. And then age is greater than or equal to 18. Age was 20, right? 20 is greater than, that's true. Actually, we already knew what it was going to be. False and true is false, right? So compare that to this one. Here we have parentheses, right? So parentheses will change the order in which things get done. So now we have a not like this, and the parentheses. That's horrible. Found is true, and age is greater than or equal to 18 was true, right? So we have true and true, which is true inside the parentheses, but then you do the not on it. So not true is false. So that's how that works. A couple more. Hours plus overtime. So we can have a larger expression, so it evaluates that out first. So hours was 45.3 and overtime was 15. So it adds those together and we get 60.3, right? So then it compares 60.3 is less than or equal to 75, which is true. Right? Here, count is greater than or equal to 0, so count is 20. Is that right? Yeah. So 20 is greater than or equal to 0 is true. And 20 is less than or equal to 100 is also true. So true and true gives you true. Right? We'll talk more about this situation here in a little bit. A is less than or equal to CH. So again, CH is a B, capital B. So that's true. So you have true and CH is less than or equal to Z. So B is less than or equal to Z. That's true. So true and true gives you true. All right, good deal. How about strings? So remember, a string is a collection of 0 or more characters. So usually it's like a word or a phrase or sentence or something like that. Technically, a string could be nothing. It could be the null string, which is the empty string. But we can compare strings to see if they're equal or greater than, less than, or whatever. And so basically what it does, it's going to go through and compare the two strings against each other, one character at a time. And it's comparing ASCII values. So it takes the first two characters and compares their ASCII values, and if they're the same character, it'll go to the next character, compare those ASCII values, and it keeps doing that until it gets one is greater than or less than or whatever it happens to be of the other one, like that. If you have a situation where one string is comprised of the other string but maybe has some extra stuff on it, the shorter string is less than the larger string. So in general, it works like you would expect the dictionary to work, okay? So that's basically how it works. But also keep in mind that it's comparing ASCII values, so case matters, right? So, an uppercase letter is always going to be lower than a lowercase letter in value because of the ASCII values. So let's look at their examples here. So, and if you download the PowerPoint presentation and look at it, there was a mistake on this slide. They had the variable declarations from example 413 on there instead. So I took those out and I typed these up. So suppose you have these string variables. So string 1 is hello, and with a capital H, right? String 2 is hi. String 3 is equal to air. String 4 is equal to Bill. String 5 is equal to big. Okay? So suppose you have those. What would the result of these expressions be? So I stuck them there at the top also, just in case we forget what things are. So string 1 is less than string 2. So it's comparing hello and hi. So it goes one character at a time. So it's not necessarily about like which one is longer, right? It goes by the character. So it's going to compare, okay, capital H. Let's see, capital H is it less than capital H? Well, it's the same, right? So it doesn't know yet. Then it's going to go to the next character. Lowercase e is less than lowercase I. That's true, right? Lowercase e is less than lowercase I, so the result is true. So that's how that works. How about this one? String 1 or str1 is greater than hen, right? So string 1 was hello. So just plug in hello for string 1 there. So capital H is greater than capital H. Well, they're the same, right? So it goes to the next character. Lowercase e is greater than lowercase e. Those are the same. Lowercase l is greater than lowercase n. That's false, right? So then it stops there. So the result of that is false. String 3 is less than an. So string 3 was air. So capital A is less than capital A. Well, we don't know. It's the same. Lowercase I is less than lowercase n. Yes, that's true. So the result is true. That's how it works. Some more here. How about this one? This is a little bit different. String 1, which is hello with a capital H, is that equal to hello with the lowercase h? No, right? So it's going to know that right off the bat. The capital H is equal to lowercase h. That's false. So the result is false. String 3 and string 4. So that's air and bill. So air is less than or equal to bill. So capital A is less than or equal to capital B. That's true. So that's easy. String 2 is greater than string 4. String 2 is high. String 4 is Bill. So is capital H greater than capital B? That's true, right? How about this one? This is one where you have part of the word in there. So Bill is greater than or equal to Billy, right? So it's going to go through one character at a time. The B's are the same, the I's the same, L's the same, L's the same. But then Bill is actually less than Billy. Because think about it, Bill would come before Billy in the dictionary, or if it was like a list of names or something. So that one's false because it's testing to see if it's greater than or equal to. And then the last one there, string 5, which is big. Big is less than or equal to bigger. It works the same way. It's going to go through one character at a time. Big would come before bigger in the dictionary. That's true. So you can use that. We can use string comparisons like that to do some interesting things, like put things in alphabetical order. If we had a big long list of names or something like that, and we had to maybe store it in an array or something, and we had to do some kind of sorting function to put those in order. Well, we can compare strings to see if they're less than, greater than, or whatever. Or maybe we're writing some kind of search function where we have a long list of names and we're trying to find a certain name in there, right? We can test to see if what we're looking for is equal to the name that we're looking at. So anyway, so you can do logical conditions, logical expressions with strings. All right, so next thing, compound or block statements with if statements. So in an if statement, if you just have an if statement, you'd say like if and then some expression and then then your action statement, else your other action statement, right? If you have multiple statements that you need to go with the if or the else, you have to enclose those inside of curly brackets, okay? And so that's what they're talking about here. So curly brackets are just used to group things together. And they have an example. I wish they had the full example in here. Like this. So if you had an if statement like if age is greater than 18, and you wanted to output 2 lines there, these 2 cout statements. Cout eligible to vote and cout no longer a minor. Else, if that was false, output these 2 lines. Not eligible to vote and still a minor, right? So you have to do it like that. What would happen if you didn't have those curly brackets? So actually, first, let's suppose that we didn't have these. So pretend like those aren't there. Okay. If there's no curly brackets enclosing multiple lines, then only the very next line is considered to go with the if or the else. Okay. So if suppose you didn't have those two lines there, and you might think, oh, it's indented, right? So doesn't that mean that it goes with the else or whatever? And the answer is no. The indentation is just there to make things more readable. So it doesn't actually determine what gets grouped with what. It's the curly brackets that determine that. So if you don't have those curly brackets in that one, that would actually compile and run. If age was greater than or equal to, if age was greater than 18, it would do these 2 things, the eligible to vote and no longer a minor. But if that was false, it would skip down and to the else and just output not eligible to vote. And that line cout still a minor, that would always get output, okay? Because if it was true, it would output those 2 lines there with the if statement, and then the next statement after that to be done would be cout still a minor. Does that make sense? So you had to be careful on that, right? How about this one? If you had didn't have those, what would happen? So if you didn't have the curly brackets that went with the if, at least on this particular case, you would actually get an error on this, okay? Because here's what would happen. It would think that, okay, if age is greater than 18, output eligible to vote, and then that next statement, see out no longer minor, it would consider that just the next statement after the if statement, right? It would be like a one-way selection. It'd be like an if that doesn't have an else, right? So it would think that it was finished with the if statement. And then it would keep going to the next statement, and it would get to that else, and it'd be like, whoa, I got an else here without an if to match up with it. I thought I was done with that if statement. And so that would give you an error on that one. So every else has to have an if that it matches up with, right? But an if doesn't have to have an else, if that makes sense. So you'd get an error saying, it would say something like if without an else, or I'm sorry, else without an if, else without an if. Does that make sense? So if you have multiple statements, you use curly brackets. So be aware of that. All right, so we can actually chain these things together. Right? They mentioned a couple of things here. This term nested. So when one control statement is located within another, it's said to be nested. And an else is associated with the most recent if that has not been paired with an else. So, and they have some other examples in the book here. I wish they had put them in the slides. Like example 418 is pretty cool, and 419. But anyway, here's an example of what we call a nested if statement. So we can kind of chain these things together. So what is this one doing? Basically, it's saying, okay, if score, which would probably be like a grade or something like that, right? If score is greater than or equal to 90, see out, the grade is A. Else, if score is greater than or equal to 80, see out, the grade is B. And so you can see it keeps going. And then finally, the last alternative, it says else, see out, the grade is F, right? So how is this going to work logically? So it evaluates, once it finds the true path, it does that, and then it skips out, exits out of the whole entire structure, okay? So suppose they made a 75. What's that going to do? So it would test, okay, 75 is greater than or equal to 90. That's false, right? So it skips to the else part, the first else, and then test 75 greater than or equal to 80. That's false. So it skips to it goes to the next else. If 75 is greater than or equal to 70, that's true, right? So it will output the grade is C, and then it exits out of the if statement. So it doesn't test to see if it's greater than or equal to 60 or anything else like after that. So that's a nested if statement. Here's another example. So check this one out. So this is testing, to see what the month is, for example. So there would probably be like an integer variable month that you assign what month it is. So just say, like right now it's September, so that'd be like a 9. And this if statement would probably keep going through all 12 months. So if month is equal to 1, notice 2 equal signs there. See out January, else if month is equal to 2, see out February, and so forth, right? So it's going to keep going. Just suppose it was March. So the first one's going to be false. So it's going to test to see if month is equal to 2. That'd be false. But then in March, 3 would be equal to 3. So we would output that and then exit out, right? So how does that differ then from this? So what's missing there? So there's the first one, and there's the second one. So on this one, there's no else's, right? So the first one, this is what we call a nested if statement. This one is just a series of independent if statements, one-way selection if statements. So in this example, it's going to do each one of those comparisons every time, right? So again, just suppose that month is equal to 3. We're talking about March. So it's going to test, okay, is 3 equal to 1? No. Okay, so don't do that. And then it's going to test if 3 is equal to 2? No, so don't do that. If 3 is equal to 3? Yes, right? So it outputs March. But then it's going to keep going. If 3 is equal to 4? No. If 3 is equal to 5? No. If 3 is equal to 6? No. So it's gonna do all those comparisons, right? They're independent if statements. So that would work. It'd probably work fine, but it wouldn't be as efficient as this, right? It's gonna basically waste some time testing all those logical expressions. So you kind of need to, make sure that you are choosing the best structure there. All right. Good deal. We've talked about this already. Short circuit evaluation. That's just basically evaluation of a logical expression stops as soon as the value of the expression is known. So we saw some examples of this earlier. I think if you go back and look at those things, I can't remember what the values were. It was age like 20 or something like that. So suppose, well, they don't tell us what they are, right? So actually say that age was 25, right? That would make more sense here. So 25 is greater than or equal to 21. That's true. And so you're going to have a true or something. True or anything is true. So it would stop there, and the result would be true. Or if grade was actually equal to A, right? I'd just say it wasn't equal to A. So it would be like grade is equal to B, for example. B is equal to A would be false. False and anything gives you false, so the result is false. So again, it doesn't waste time evaluating the right-hand part if it can determine what the result is going to be. Here's something I should point out. Also, we've never really had a problem in this class with this, but I should mention it. The book mentions that you need to be careful when comparing floating point values for equality, because you might run into a situation where things could be near equal but not exactly equal. And so here's an example. And this can also depend on your compiler. Like, some compilers are more accurate than others as far as like, how many decimal places they go out and stuff like that. So suppose you have something like this. You're testing to see, okay, is 1.0 equal to 3.0 divided by 7.0 plus 2.0 divided by 7.0 plus 2.0 divided by 7.0. We know mathematically that 3/7 plus 2/7 plus 2/7 is 7/7, which is 1, right? But 3/7 and 2/7 is they're these repeating decimal irrational number things, right? So they kind of, if you actually do it out to see what they are, I can't remember what they are. What 3/7? 3.0 divided by 7.0 is 0.428571, and then it repeats, right? 428751 or whatever. So it repeats and goes on forever, right? 2/7 or 2.0 divided by 7.0 is 0.285714 repeating, right? So anyway, the point is that inside the computer's memory, that repeating decimal action can't go on forever. because the computer's memory is finite, right? So at some point in time, it's going to cut it off. And so you might end up with something like, instead of 1.0, you might end up with something like 0.999999, something like that, right? Which technically is not equal to 1.0. So that's what they're talking about there. You could have something that's near equal, but not exactly equal. Excuse me. And they mentioned a couple things that you can do, like a fault tolerance check. But again, we've never really had a problem in this class with that. But at the same time, we're not doing something like programming a satellite that's going to Mars or something like that. That might be, more important for that. All right. Okay, how about this situation? This is important for me to talk about. Suppose you have some variable and you want to test to see if it's within a certain range. Okay, so you might think I can do it something like this. Suppose num was our variable, right? And we want to test to see if it's between 0 and 10 inclusive. In mathematics, we've seen stuff like this before, right? 0 is less than or equal to num is less than or equal to 10, right? But you can't write it like that in C++ and expect it to work correctly, okay? You can actually write that. It won't give you an error, but it will always evaluate to true, no matter what the value of num is. And so why is that? Well, here's actually what it's doing. So remember that true is a 1, false is a 0, right? So that's what it's going to return when you test stuff. So let's see here. Suppose that num is 5, which technically is within that range we're probably wanting to test, right? So it's testing. Okay, is 0 less than or equal to 5? Is that true or false? That's true, right? So it returns a true, but what's actually returning? A 1, right? Remember 1 is true? And then it's going to take that 1 and compare it against 10. 1 is less than or equal to 10 is true, right? So it returns a 1, basically, which is a true. So you're going to get a true out of that. How about if num was not within the range? So just say 20. It works the same way, right? 0 is less than or equal to 20. It's true. So again, it returns a 1. And we do the same thing. 1 is less than or equal to 10. It's true. So you think that you could write like that, but you can't, right? You're always going to get true. Even if it's a negative number, just plug in a negative number. Like a negative 5. Negative 5, it'd be like 0 is less than or equal to negative 5. That'd be false, right? But it would return a 0 for false. And 0 is still going to be less than or equal to 10. So you always get a true out of that. So you can't write it like that. You basically have to break it out into two parts. So you'd have to do something like, you could write it 0 is it less than or equal to num? And you put and between them, and num is less than or equal to 10. You have to break it out into two pieces like that. And there was actually a couple of examples that actually did that earlier. You could write it in different ways, right? You could have written it num is greater than or equal to 0 and num is less than or equal to 10. There's different ways to write logically equivalent if statements. So anyway, just point that out. All right. Let's see, what else we got? Here they mention a few other things to watch out for. you have to have parentheses around if statements, around the outer expressions, and don't put a semicolon after the logical expression. I've mentioned that already. Okay. Let's go on. Here they're talking about how you can test the input stream for input failure mode. That's what I showed you guys the other day, right? Because if it goes into failure mode, it just kind of cuts it off. So remember the other day with our files, I showed you how to do this, how to do something like, what is it, if not in file, sorry. Like that, remember that? If not in file. So you can test it, right? So it returns, that would return true if the file had gone into input failure mode, right? If you do if in file, it's going to return true if everything's fine, false if it couldn't be opened, right? So I did something like if not in file, return 0, right, to end the program. Like that. So that's what they're talking about there. How about this? This is a common mistake. It's so easy to, it's such an easy mistake to make, but not an easy one to necessarily to find. Okay, so and this will compile. It won't give you an error or anything. So what's wrong with that? If x is equal to 5, see out the value is 5. Right, exactly. Remember, when you're testing for equality, you put 2 equal signs. So it should have been if x equal 5. So it doesn't give you an error. It actually, in there, it's actually going to assign 5 to x. And whatever the results, or in it, it'll actually do that, right? So whatever x was before, it's now 5. So just be really careful and don't do that. All right, a few more things in the chapter. There's this thing called the conditional operator. I hardly ever use this, but C++ supports it, and some other languages have it too. It basically looks like this. So you've got a question mark and then a colon, and it's kind of a shortcut way of writing an if statement for certain types of situations. It comes in handy. So the way that you do it is you put the expression, the logical expression, the test part, you put that, and then a question mark, and then you have your true path, and the colon, and then your false path. So you would use it in this way. So they have an example down here. Max is equal to a greater than or equal to b, question mark, a colon b. So what that does is it's going to test to see if a is greater than or equal to b. If that's true, it will assign a to max. But if it's false, it's going to assign b to max. Does that make sense? So you can always write that as an if statement, and that's probably what I would do. I'd probably write, if a is greater than or equal to b, max is equal to a, else max is equal to b. That would do the same thing. I guess that's the shortcut way of writing it, but I think I don't know. I like if statements better. All right, a couple of other things here. Here they mention about indentation. Again, indentation can make your code more readable, but technically it doesn't determine how things get executed or anything like that. So you always have to, if you have multiple statements inside of an if or an else, you have to put those inside of curly brackets to group them, right? And then it makes it more readable if you indent inside of there. They mention about 2 different main ways or main styles to do in your curly brackets. First way is you can put each of the open and closed curly bracket on a line by themselves. That's what I do. That's how I like to write them. But you might see in some examples, they'll put the left brace after the expression, and then the right brace or the right curly bracket on a line by itself. So what they're saying there is, in the second version, it'd be like if, and then whatever, and then open curly bracket there, and then close curly bracket there at the end. So that's one way of writing it. I like putting them both on separate lines by themselves, like that. All right. Using pseudocode is useful. All right, how about this one? Switch statements, right? So a switch statement is another way of writing a conditional or selection structure. And it comes in really handy for one type of if statement situation. Maybe where you're testing the same thing over and over again. Let's see. Maybe something like if you're saying, this would be equivalent to this. If grade is equal to A, see out, grade point is 4.0, else if grade is equal to B, see out, the grade is 3.0, else see out, else if grade is equal to C, see out, the grade point is 3.0. So in that situation, we'd be testing grade over and over again for an equal value. This is a perfect kind of situation for a switch statement. So here's how a switch statement works. You have the word switch, S-W-I-T-C-H, and then inside of parentheses, some expression that evaluates true or false, right? The logical expression part. And then you have different cases. And then, so you have the word case, and then after that is the actual possible value for each one of those things. If it's a number, you put the number there. If you're talking about a character, you put the character there inside of single quotes. One limitation with switch statements in C++ is that they don't work with strings. So you can't put strings there in a switch statement. You'd have to use an if statement to do that. And then at the end, you have an option of having what's called a default. A default is like a last case scenario. If it doesn't find a match on any of the other cases, it skips down to the default. The default is like the final else in a nested if statement. And then notice they have break statements in between each of the different cases. Okay, so the break statement will, once it finds a match, the break statement will make it exit out of the switch statement. If you don't put a break statement, it just keeps going down through the different statements. So we'll do some examples of these things to get some practice. Here's a flowchart for that. Here is an example. So suppose we were talking about a character variable like grade, and so we could write a switch statement like this: switch grade, case, capital A, and then a colon, see out the grade point is 4.0, and break. And then case B, see out the grade point is 3.0, break. So what it's going to do there, whatever the value of grade is, it's going to look for a match for that. So suppose the grade was C, it's going to skip down to case C, and output the grade point is 2.0, and the break statement will break out of it. Suppose they entered the letter S, or P, let's just say P, for grade. Well, there's no case that has P, right? So it's not going to find a match, so it's going to go down to the default. In the output, the grade is invalid. And notice, you don't have to have a break after the default there at the end, because it'll just go into the next statement after anyway. So it's just a different way of writing one type of nested if statement, if that makes sense. Does that make sense? And so I don't know that it's really all that much less to type, but it might be easier to look at and see what's happening in that situation. Does that make sense? So I can just kind of glance at that and say, oh, okay, it's looking for a match for the grade. All right, so that's a switch statement. All right, I think I said that already. All right, here's something that we probably won't use this semester, but they mention it here at the end of the chapter. And so this thing called the assert function. So basically what this is, it's a way of testing a certain situation to make sure that you've done something correctly, and if it doesn't pass this assertion test, it will exit out of the program. So they mention here that certain types of errors are difficult to catch, such as the division by 0. So what happens when you divide by 0? It's a bad thing, right? So it's like undefined, right? It destroys the universe or whatever. Not necessarily, but you know, basically if you try to divide by 0 in your program will crash, right? So that's basically what will happen because you can't divide by 0. And so if you wanted to test for that, you could always just write if something is equal to 0, return 0 and exit out, right? So you could test for that just with an if statement. But this is another way of doing that. So they say the assert function is useful in stopping the program execution when certain elusive errors occur. And so you just do something like this. You'd put the word assert and then the expression that you want to test, and then actually a semicolon, and then some statement afterwards. And if the expression evaluates to true, it will actually do the next statement, but if it evaluates to false, the program will terminate, and you're supposed to get some kind of error message on the output screen. And they mentioned to use the assert function, you have to include C assert with your header files at the top. And assert is useful for enforcing programming constraints during program development. But then, after you're kind of done testing and debugging and stuff like that, you'd probably want to get rid of those assert statements. So you could either go back and delete them all, but if you had like a whole bunch of them, you could just put this line up there after your include files that says number define in debug. And if you put that there, then it won't do all the assert, any assert commands that you have. It won't do those. It will disable them. So, like I said, I don't really use this, but it's in there. All right. So that's pretty much it from this chapter. So we talked about control structures. We talked about relational operators. We talked about logical expressions and logical operators, different forms of the if statement, one-way selection, two-way selection. We talked about, ifs and else's. We talked about curly brackets and how I can use those to have groups or blocks of statements. And we talked about the switch statement and the assert function.